Today we're going to be looking at the relationship between power and Hamming weight. Basically how the bits a chip set shows up in a power trace and how we can measure that leak. This is the bridge between dynamic power attacks, like we did in the last episode, and the correlation power analysis attack we're building towards. We'll stay hands-on with the ChipWhisperer, but now with a more realistic leakage model instead of just a single bit. A quick recap of last episode with dynamic power analysis. We assumed that a single key dependent bit flipped the power trace enough that if we group traces by that guessed bit, we could recover an AES key. It did work, but it was a pretty crude view of what the hardware is actually doing. In this lab, we upgrade the model and say power tracks the Hamming weight of an internal byte. So all 8 bits matter, not just one. We'll learn what Hamming weight is, where the S-box output shows up in the trace, and how to plot power versus Hamming weight so we can literally see the leak we're going to use for correlation power analysis next. Hamming weight is relatively simple because it's just how many 1 bits are set in a value. If our byte is 0x53, the binary representation has 4 1s, so its Hamming weight is 4. This matters because every AES S-box output is an 8-bit value, so its Hamming weight is always between 0 and 8. If the chip's power depends on how many bits are set in that byte, Hamming weight becomes a leakage model we can actually predict from plain text and key guesses. Hamming weight is something that can help leak information. When the CPU writes a value into a register or a bus, it's physically flipping transistors from 0 to 1, and each of those transitions costs a bit of energy. More bits set means more current drawn at that instant. So the power at that moment carries a faint fingerprint of how many bits were just written. With DPA, we only watched a single bit and did a two-way split. The Hamming weight we use all 8 bits at once. Intuitively, setting 8 bits costs roughly 8 times what setting 1 bit does. So this richer model supports stronger, more reliable attacks like correlation power analysis. And so step 1 is to reuse the AES S-box model we already built in earlier labs. We have a helper function, AES internal, that for a given plain text byte and a key byte returns the S-box output value we believe is leaking the trace. That output byte is exactly what gets written to a register during AES. The notebook sanity checks this model with a couple of test vectors. AES internal AB, EF should be 1B, and that AES internal 2201 should be 26. Once those asserts pass, we know the math that feeds our leakage model is correct and we're safe to move on. And next, we'll then implement Hamming weight in Python. The easiest way is just with bin.count. It converts the number to a binary string and then counts the ones. The notebook wraps that in a calc Hamming weight function and then pre-computes the Hamming weight for all 256 possible byte values. That gives us a lookup table, HW, where, for example, HW53 equals 4, meaning 53 has 4 1 bits. From now on, any S-box output we compute can be instantly mapped to its Hamming weight just by indexing that table, which is much faster than recomputing it on the fly for every trace and every guess. Once we have Hamming weights for every trace, the first idea is let's color the traces by the Hamming weight of their SBox output and see if the patterns separate. So we plot, say, the first 2,000 samples of each trace and color each trace according to its Hamming weight. But in the raw data, the leak is tiny compared to all the other activity in the chip, so the SBox related differences are basically buried in the noise. This slide is showing that if you just overlay color traces directly, you won't see much. We need more signal processing to tease the leak out. The fix is to remove the common shape that all traces share and keep only the piece that depends on Hamming weight. First, we compute the overall average trace of the entire dataset, which is what the chip's baseline activity looks like with all the data variations averaged away. Then we group the traces by Hamming weight value from 0 to 8, average within each group, and subtract the global mean trace. What's left in each group is a tiny waveform that represents the Hamming weight dependent part of the power. When you plot those mean minus mean traces, the SBox leakage suddenly becomes visible. Once we've done that mean subtraction trick, there's usually one very clear spot in time where the colored curves fan out. Let me pause while this ad plays through.
Just a suggestion. Because there are car emergencies, unplanned stops, and speed bumps in your area. Orlando, there are drivers in your area. Uber, request a ride today. Wait time varies, terms and conditions apply. See app for details.
Alright, like as I was saying, once we've done the mean subtraction trick, there's usually one very clear spot in time where the colored curves fan out. That's when the SBox output is being written. Instead of eyeballing it, the notebook finds it automatically. It computes the absolute difference between one Hamming weight group's average and the global average, and then takes the NP argmax to find the sample index with the largest deviation. That index is stored as SBox location. For each Hamming weight group, we can then read Hamming weight averages. To get the measured power at that exact moment, the SBox output hits the bus. Now we take those 9 values, the measured power at SBox location for Hamming weights 0 through 8, and plot them against Hamming weight. The beautiful result is that the points fall roughly on a straight line. Higher Hamming weights correspond to a steadily different average power level. That linear relationship encodes our leakage model. Setting 8 bits costs at about 8 times the energy of setting 1. Correlation power analysis' entire trick is to predict Hamming weights from guesses of key and plain text, turn those into predicted power values, and then look for the key guess whose predictions correlate best with real traces. On most ChipWhisperer hardware, the line we just saw slopes downward instead of upward. That's not because the physics are different, it's because of how we measure current. We put a small shunt resistor in series with a microcontroller's supply and measure the voltage drop across it. As more current flows, the drop across the shunt resistor increases, but since we sample only one side of that resistor, the voltage at our measurement point actually goes down. So higher Hamming weight means more current, more drop, and a lower measured voltage, which shows up as a negative slope in the Hamming weight versus power plot. The ChipWhisperer Nano is a special case because it has an inverting amplifier on its measurement input. That hardware inverts the sense of the signal, so now higher Hamming weight actually shows up as a higher measured value. The slope flips to positive. Same underlying physics, just inverted by an analog front end. The practical lesson is always confirm your hardware slope before you start implementing these plots. If the slope comes out backwards relative to what your theory expects, you can compensate in software by simply negating the traces. but you need to be aware that your board might be flipping that sign. And to zoom out for a second, this is how the traces feeding all of this analysis are captured in the hardware notebook. We pick a scope type, platform, and crypto target, build and flash the AES firmware, and then run a loop where we arm the scope. Send a plain text over simple serial protocol, capture the power trace, and store it. The key is fixed in the firmware, but for each iteration we feed a fresh random input that gives us about 1,000 traces, each with a known plaintext, the same secret key, and one measured waveform. Later in the main notebook, we use that information to compute S-box outputs, compute their Hamming weights, and link them back to specific points in the trace. And so we've gotten to the end of this presentation. So to wrap it up, we formalized Hamming weight as count the ones and showed its useful per byte measure of how much data is being sent inside the chip. We then demonstrated that the power consumption of the S-box write instant tracks the Hamming weight in a roughly linear way, and that we can automatically find the S-box location in the trace with argmax. And that gives us a clean quantitative leakage model. Predict Hamming weight, predict power, and match against traces. We also saw that the sign of the slope depends on the measurement front end, especially on the Nano. So you always have to know your hardware. So I'm going to go ahead and launch the Jupyter Notebook server now. And go to the course within Jupyter folder, courses, Side Channel Analysis 101. So I'm going to pull up both the hardware and the main notebook. So this is the hardware support notebook, and it's not a standalone tutorial. It just handles hardware setup and trace capture, and the main notebook picks up from there. But I'm gonna have to put some of the stuff here from the hardware notebook inside the main notebook. So I'm going to say hardware setup and trace capture. Set that to markdown. Then we're going to take these scripts.
Smartwater knows that everything's asking for your attention, and focus is a choice. You're moving between tabs, tasks, thoughts, all at once, but you decide what gets your energy. That's when you reach for Smartwater, with a pure, crisp taste that keeps up and a bottle that says you choose well. Because what you choose says something, and choosing to look after yourself says a lot. Smartwater, for those with a taste.
All right, we're going to set scope type to CW Nano, set the platform also to CW Nano. We can leave crypto target equal to tiny AES 128C. and simple serial version to the version 2. Let's go ahead and run that. There. Not sure why that's happening. Just gonna go ahead and reset the kernel. And unplug the device. Plug it back in. Run it again. Okay, that fixed whatever problem we just had. Alright, now we're gonna run this capture loop. So the ktp.basic is ChipWhisperer's key text pair generator. It gives us a fixed key but random plain text. We're gonna do 1,000 AES encryptions, where we set n to 1,000. And so each loop is going to arm the scope trigger, send the plain text to the target, capture the power trace, read back the ciphertext just to keep the protocol happy, then store the trace and the plain text. There's going to be a progress bar also that will show us how far along we are. And it's important that the key stays fixed because it means that the only thing changing between traces is the input plain text. So once the capture is done, we can disconnect cleanly using these commands. Target disconnect. Let's go ahead and run this. that ran successfully. We're going to go ahead and disconnect. I'm going to delete that cell. Delete that cell. I'm going to add a variable in here. A version. Set that equal to hardware. The way that I just did that is, I'm not sure if it's just the way that I've been learning how to interact with these labs, but I have kind of gone back and forth between the hardware and the main notebook, and there are two different kernels, so I just copied everything over from the hardware notebook into the main notebook, but I didn't need to copy everything over. I can just set this version equal to hardware, and then in another cell after, we have this condition we can run where if we're running hardware, then it just runs the hardware notebook. Right, so then I can delete these. For some reason I can't delete this though. Okay. So we're gonna run this, and we're gonna run this. Alright, so it's going to perform that trace capture again, and then it's going to disconnect the scope and the target. So for the AES model, we'll be looking at the S box again, so grab your implementation from the last section. Alright, before we do that though, let's go ahead and plot the traces that we're capturing. All right.
Progress starts with purpose. We question what's possible and seek bold ideas, because everyone deserves a brighter future. Vanguard, innovation that lights the way. Visit workplace.vanguard.com to learn more. All investing is subject to risk.
All right, for our AES model, S-Box, we have from our previous lab. And we also have the AES internal function, which receives input data and key, and then XORs those two parameters and provides us with an S-box output. So here are two simple test vectors. If you get the checkmark printed all okay, then we can move on to the next step. Alright, we're good. Recall that the reason that there's a relationship between power consumption and a microcontroller's internal data is that setting this data takes power. We've also seen that the more data that is set, the greater the average power draw. It's not far-fetched, then, that there should be some sort of consistent relationship between the number of bits set to 0, or set to 1. So it's not far-fetched, then, that there should be some sort of consistent relationship between the number of bits set to 1, called the Hamming weight, and the power consumed by doing so. Hamming weight, despite a pretty simple idea, isn't actually trivial to calculate. You can write a function to do this, but in Python it's far easier just to convert to a string of bits and count the ones. Even better, create a lookup table, also known as do the calculation for each number between 0 and 255 and stick them in an array. So we're going to set hardware, or Hamming weight, equal to bin count the ones. For n in range 0 to 256. And let's get the OK to continue. Our first issue is that we run into what we don't know where the SBox operation is happening. It should be happening pretty close to the beginning. Let's guess and say within the first 2,000 samples. One thought is that we could group the traces by Hamming weight and assign a color to each one. If we plot that, we might also be able to find a pattern. Okay, you'll probably find that this plot doesn't really tell us much. The part of power consumption associated with the SBox output is just too small to pick out. We could try averaging the Hamming weight groups to make things more distinct, but that doesn't solve the fundamental issue of the SBox output being lost in the noise of everything else that's happening on the chip. Instead, let's approach this from a different angle. Really, what we want here is to remove the overall shape of the trace and just leave the signal from the SBox output. We could just pick a trace and subtract it from the group. By subtracting an average of all the traces instead, we'll make the plot more distinct. Even better would be to have an even weighting between all of the Hamming weight groups, since the extreme Hamming weights 0 and 8 are far less common than the middle values. But this won't end up being super necessary, though you can still attempt this if you'd like. The plot will also be more distinct if we average all the Hamming weight groups to remove any outliers as well. Try implementing this. We'll again handle the plotting for you. Okay. So we're going to call output notebook. Then we're going to set p equal to figure. Then we're going to create Hamming weight groups. 1, 2, 3, 4, 5, 6, 7, 8. And 9.
For all the things you have to do and places you need to be, let Uber take you there. Because that check engine light isn't just a suggestion. And because flat tires won't get you anywhere. Because there are car emergencies, unplanned stops, and speed bumps in your area. Orlando, there are drivers in your area. Uber, request a ride today. Wait time varies, terms and conditions apply. See app for details.
Plotting this, you should get a very distinct spot where the colors separate. This is where the S-box operation is occurring. In fact, it's probably distinct enough that you can choose the S-box location solely by where the graph is largest. Can't serialize. You can choose the S-box location solely by where the graph is the largest. See, it's larger down here. That's some funky looking behavior. Now that we know where the S-Box operation is happening, I mean, I suspect it's happening. I don't really know what's happening based on this. I mean, some of these green colors very distinct spot where the colors separate. So where the S-Box operation is occurring, in fact, it's probably distinct enough that you can choose the S-Box location solely by where the graft is the largest. The graft is the largest up here and down here. Hey, you may want to convert your Hemingway averages to NumPy array to allow you to access by column. Hardware, I keep saying hardware. Hemingway averages will give you Hemingway averages at the S-Box location. Okay, so here we have the following. Output notebook P is equal to figure. So we're just creating another graph, I guess. You should find that the relationship is mostly linear, which probably won't come out of left field. It makes sense that by setting 8 bits will roughly take 8 times power that setting 1 does. You'll also find that the slope of the relationship is negative unless you're on a ChipWhisperer Nano. This happens for a good reason. If you remember how we are measuring the current into the device, you'll find that the voltage will go down for an increase in current. You can see this in the following figure. For the ChipWhisperer Nano, the slope is positive due to the presence of an inverting amplifier of the input of the measurement port. We are measuring the drop across the shunt resistor. An increase in the current causes a higher voltage across the resistor. When no current flows, there is no drop across the resistor. But since we only measure a single end of the resistor, we see a higher voltage with no current flows. We can't fix the slope by simply inverting the measurement direction. Now that we know where the S-Box operation is happening, try going back to the original plot and zoom in that section. Can you find out the difference between the Hemingways now? With this lab, we should be reasonably convinced that there is a linear relationship between a Hemingway of data being set in a microcontroller and the power it consumes from doing so. In the next lab, we'll see how this can be used to greatly improve our dynamic power analysis attack. Yeah, I mean, sure, I guess, you know, like, I see a lot of that purple stuff going on there. Alright. Then we've got the green. The green spikes are higher. Is that where the S-Box operations occurred? These are, okay, yes, these are 2,000 traces. Right? Alright, so we're just moving along through these labs just fine. We're not running into any issues with dependencies.
Save on organic,
so things to be working just fine.
Get a 16-ounce container of organic.
Let's take a look at the next lab. So next lab we'll be doing CPA on firmware implementation. This next one looks pretty interesting. I'm sure we'll get through it just fine, just like we've been getting through these other ones. I enjoy having labs to go through. It's definitely good to have experiments that I can get through from start to finish. I mean, I definitely don't understand everything that I'm doing in these labs, but as I go back and do them again, I start to understand more and more what's actually happening. Starting to understand this model as well with the S box. So these two parameters are XORed with each other, and that produces some kind of S box output. So what is it? I think if you XOR, what is 63 XOR by 16? (63 XORed by 16 gives us 75. So where's the 75? Is it in here somewhere? Yeah, it's right here. So if we were to have input data of 63 XORed with 16, it would produce S box output of 75 right here. And if you XOR 0x75, XOR the input key, and in this case it was 16. You should get 63. Yeah. All right. Well, I guess that's it for this lab. It was a short one. Learned a couple things, so look forward to the next one. Thank you.